is too big and it takes time, but I will respond to each of your mails. I'm very, very, very positive and very sure. So let us dig into what we have prepared for today. We've been looking at, we introduced vectors, and the vectors of pure mathematics, not the vectors of paper 2. In paper 2, you will also study some vectors here. We are discussing vectors, parts of vectors which are taught in pure mathematics 1. And last time we were looking at the basics. We discussed about the dot product, and then we had started discussing on the cross product. We had defined the cross product of two vectors, that is A cross B, as the vector magnitude of A times magnitude of B times the sine of theta, and then times n cap. And of course this you know it, this you know it. This one we said this is the angle between the vectors A and B. That's the angle between the vectors A and B. And this guy here, we said this guy is normal to both A and B. He is a unit vector normal to both A and B. That means he's perpendicular to A and he's also perpendicular to B. And he's a unit vector. In other words, he has magnitude 1 unit. Now, some of the properties of the cross product is that for it, it is not commutative. It is not commutative. Remember, the dot product was commutative. With the dot product, we had that A dot B is the same as B dot A. We had commutativity. But the cross product is not commutative, and the A cross B is equal to negative of B cross A. To prove that, you may need to get back the definitions of the cross product. You could use the determinant definition, and then you try to prove that you are actually getting that. Try to look for this guy and try to look for that guy. You'll find that one is the negative of the other. Then it is also obvious that A cross B is normal to A and B. This is obvious because this is a vector. This is a vector, and since it is in the direction perpendicular to A and it's in the direction perpendicular to B, then this vector is perpendicular to A and it is also perpendicular to B. That is very obvious. In other words, when you get A and you dot it with this guy, you'll pull out this constant, the magnitude of this vector, and then you'll need to dot A and n cap, but A dot n cap is 0. So the same thing with B, B dot n cap is 0, and so A cross B is normal to both A and B. Then we have A cross A is 0. That is obvious because the sine, the angle between A and A is 0, so the sine of 0 is going to be 0, 0 times this vector here. We shall end up with the 0 vector, not the 0, the number, but the 0 vector. That vector, all of whose entries is 0, zeros, all of whose entries are zeros. Then property 4, we are saying that this guy here is the area of the triangle determined by the vectors, this and that. Well, that is also very obvious. If we have these two vectors, we have, if this is the vector A, and then this is the vector B, then we are talking about that triangle there. Remember, if here we have that angle as theta, that's the angle between the vectors A and B, then we know by definition from your trigonometry that the area of that triangle is given by a half magnitude of A times magnitude of B times the sine of what? Times the sine of theta. But then now let us also look at this guy here, A cross B, the magnitude of that guy. You will clearly see the magnitude of this vector here. It is just this one here, magnitude of A, magnitude of B, sine of theta. That's the magnitude of this vector A cross B. And so you can see a relationship. So if I call this equation 1, I call this equation 2, it is very obvious that when you use 1 and 2, you'll find that the area is that guy there, A cross B. So that's the area of the triangle determined by those two vectors there. If you remove this half here, then you're multiplying this thing by twice, so it is kind of the area of the parallelogram. So, which means A cross B, magnitude of A cross B alone is the area of the parallelogram determined by these two vectors there. I was just interested in the triangle. Then we have these other properties where you're crossing the unit vectors here. You see, we said I cross J gives you K. You guess this Y. This is the unit vector in the direction perpendicular to these two guys. You remember Fleming's law? Yeah, if this is I, this is J, then the perpendicular is definitely supposed to be K. Those who did some physics in magnetism, you always saw when the current is perpendicular to this and all that kind of thing. So in mathematics, some nice things like that appear there. However, of course, we can use the following figure. We can use the following figure to find the other properties of 5. You see here we just picked out I cross J and then J cross I. But how about I cross K? What do you get? You didn't want to write a lot of them here so that you don't cram. That there is a figure we can use to get those products there. It's a simple figure, something like a circle, whereby this is I, and then we have this as J, and we can have this as K, the unit vector. So we move clockwise around that figure. So that means if you move anti-clockwise, then you are opposing. So if I want, for example, I cross J, have something like I cross J, then that is going to give me K. Then if I want J cross I, I'm opposing that. So J cross I, I'm opposing. So it is going to give me K, but the K is negative. But if I want J cross K, I'll have J cross K. J cross K is going to give me I. J cross A, I didn't oppose my direction. But what if I want now K cross J? K cross J, I'm opposing, so it's going to give me negative I. Then you can now try to tell what K cross I is and I cross K, now that you understand the dynamics of that figure there. So let's pick a few examples on which involve using the cross product. We saw how to find a unit vector normal to two vectors using the dot product. Now we are also going to see how can I find a vector normal to two vectors using the cross product. So find a vector, normal, find a vector normal to I plus 2J. Let me name this, let this be A. I plus 2J, and then minus 3K, and B equals to negative 2I, and then plus 3J, and then plus 5K. So we want a vector which is normal to both of those. So we can use this property here, that vector should be A cross B. And so in other words, they are like telling us to find the cross product of this guy and that guy there. So we could either use the determinant method, which we wrote down. So we are saying that A cross B. By the way, you could also, even B cross A would work, B cross A. It would be also perpendicular to both of those guys. So A cross B, the only difference would be that they are in opposite directions. They are parallel. A cross B and B cross A are parallel, but in opposite directions. And they are equal in magnitude. So A cross B using the determinant method, let's call this maybe method 1. This should be equal to the matrix, the determinant of the matrix, I, then J, and then K. We put the coefficients of A, and that is 1 to -3 and to -3. And then now the coefficients of B. We have this definition. We saw it in the previous discussion. 3 and then 5. So how do you find the determinant of a 3 by 3 matrix? We shall write that I, but then we need the coefficient. To get the coefficients, the determinant of the matrix, you're going to remove the column containing I and the row containing I. So we remain with this. That is 2, -3, and then 3, 5. Then when we come to J, you introduce a minus. What is the coefficient? What's the component in the Jth direction? So we remove the column containing J and the row containing J, and we remain with 1, -2, and then -3, 5. And then now plus, when we come to K, it's plus. So this was minus, plus, was plus, minus, and then plus. So plus K, remove the column containing K. This is what we remain with, which is 1, -2, and then 2, 3. So this is going to be equal to the determinant of this matrix. Now this is a 2 by 2, so the determinant is easy to get. This is going to be 10 minus -9, that is 19i. And then this is 5 minus 6, 5 minus 6 is -1. It means this to be +1. Then this is going to be 3 minus -4, that is 3 plus 4, and that is 7. So that would be using the determinant method. The other method is you could choose to multiply directly using this guy here. So how would we do that? We would say A cross B. This is going to be equal to, we have -I, we have I plus 2J minus 3K. We are crossing it with -2I plus 3J and then plus 5K. So what are we going to get? We will get this and multiply with everything here. Then we get this, multiply with everything here. Get this, multiply with everything there. So we have this and that. We have we are multiplying I, and we are crossing it by the vector -2I. So this is like you're crossing I and I, which is just going to give us 0 with the -2 there. So this is going to vanish. And then this and that, we have I cross J. if you draw your diagram, we have I, J, and then K. So I cross J is a positive K. So we are getting this with that. That is a positive K. And then we have 2 times 3, which is 6. So we already have 6K. Then we come to get this and that. I cross K. I cross K, that is negative J. So minus J. But we have the coefficients 1 times 5, which is just 5. So minus 5J. Then we come to this J and the I. J and I, that is negative K. So J and I negative K, but we have this and that, that's negative 4. But when we multiply it with negative K, it becomes positive 4K. Then we have J and J, that's a 0. Then we have J and K. J and K is I, positive. J and K is I, but we have 5 and a 2, which is positive 10, positive 10I. Then we come to this guy here. I'm going to need this diagram. So we have K and I. We are now here. K cross I, that is positive J. So we have positive J. It's positive. But then we have this and that, which gives us positive 6. And then now we also have K cross J. K cross J, K cross J, that is negative I, because we are opposing, K cross J, negative I. We are here. We had K cross I, that was positive J. And then we have K cross J, that is negative I, K cross J, but then we have 3 times negative 3. So we also have negative 9 multiplying, which is just positive. So plus 9I. And then we have K cross K, which is a 0. So you try to simplify the things. We have K and then K here. Oh, I don't know, there must have been some slight mistake, but you'll try to follow. I always love this one better than this one here. Try to follow through this one. There might have been some problem somewhere, because I'm seeing 6 and then 4. I don't see any other I's. The J's, I have negative 5, and then the minus, the negative 5 and the plus 6. So the J's have come out. Already the J's we have negative 5 and then 6, that is plus J. And then the I's we have 10 plus 9. Those are the 19 I's. And then the K's, they are not coming out nicely the way I want them. I'm having 6 plus 4, which is plus 10, plus 10K. These vectors are supposed to be the same. So check where the problem is. It comes when we are multiplying something that brings out a K. The things that bring out K, what are they? We have I cross J, and then J cross I. Where do they come from? This and this. Those are 3. Those are 3. These are 3, but they are positive. They are positive. And then we also have this and this. Those we have -4, and then yeah, it comes out when we were getting this. That's where the problem was. These are 3. We have, these were 3. This and this, they were 4, not 6. And so I think everything is now okay. Yeah, this thing needs someone who is very, very, very careful. You can choose the one which is quick enough for you. But all those are methods we could use to find the cross product. Now, let's pick some other example. Simple one. Another application of the cross product. Example. Find the area. Find the area of the triangle with vertices. And the area of the triangle with the vertices A. Then this is going to be 2, 1, -1. B, which is 2, -1, 2. And C, which is 7, 4, -1. So in our solution, we could try to sketch the triangle. This should be A, B, let that be point C. So we are looking at that triangle there. So we shall assume that that's the triangle determined by the 2 vectors, AB and then SC. So we find the vector SC. The vector SC is, of course, OC minus OA. And so this is going to be equal to 7 minus 2, which is 5, and then 4 minus 1, which is 3, and then -1 minus -1, which is 0. And then we could also find the vector AB, and this is going to be equal to AB is OB minus OA. OB minus OA. So that is going to be 2 minus 2, that is 0. -1 minus 1 is -2. And then 2 minus -1, that is 3. So you're going to have to find SC cross AB in your free time, so that the area now would be equal to 1/2 of the absolute value of SC cross AB. So when you get this vector, get its magnitude. We know how to get the magnitudes of those things, and then you get yourself the area, and that will be in square units. So now that you are an expert to compute the cross product, you will complete that. So the area will be equal to, you are required to complete. I should give you a question to try out in your free time. The points. Zero, 3, and then -4. The points that this, which is 2, -1, 2, and C, which is 7, 4, 0, 3, 4. Nope. This should be 2, 1, -1. I don't want to repeat the same question I had given. Then 6, 4, -3. 3, and C, which is 14, 7, negative 6, lie on the surface of a table. Find a vector normal to the surface. Find a vector normal to the surface. So that you'll try out in a time when you're feeling a little happy. Now there is something I want to emphasize, something that came to my attention through, in fact, one mail which was sent to me. Somebody was asking for more emphasis on this. To prove that A, B, and C are vertices of a triangle, one may prove one of the following conditions. Of course, they are not exhaustive, but I want to give those which lie within the things which are at our level. So you could prove one of the following things. Last time we looked at the cross product. So how can I prove that A, B, and C are vertices, the dot product? How can I prove that A, B, and C are vertices of a triangle? Now for A, B, and C to be vertices of a triangle, the general issue here is they should not be collinear. The moment they are collinear, in other words, the moment they lie on the same straight line, then they don't form vertices of a triangle. But the moment we offset any one of these points from that line there, however small the perturbation is, however small the offset is, then they form a triangle. In other words, for these points here in higher mathematics, they use the word affine independence. For these points A, B, and C to form vertices of a triangle, they must be affine independent. They shouldn't lie on the same straight line. So here all you're trying to prove is that these points are not collinear. So how do we do that? Using the cross product. We know by the dot product. By definition, A dot B is given by magnitude of A times magnitude of B cos of the angle between these two guys here. Cos of, were we using the dot product? Yeah, we were using the dot product. Cos of theta, where theta is the angle between these two guys. Now, if these points are not to be collinear, then the vector AB must not be parallel to the vector BC. In other words, the angle between these two vectors here, theta, should not be, it shouldn't be 0, and it should not be 180 degrees. Of course, it is 180 degrees if C is in the middle here. But in this case now, the angle between these two guys is 180. AB, it's 0. Now, if C is in the middle here, that's when we have that direction, then the angle between them will be 180 degrees. So we shouldn't have that case. So the condition we derived from this was that A dot B, because we know when theta is 0, we have cos of 0 being equal to 1, cos of 0 degrees. And then we know that the cosine of 180 degrees, this is equal to negative 1. So A dot B should not be equal to plus or minus, and then you bring this magnitude of A and then times magnitude of B. That was the first condition we had. Yeah, unfortunately there was an omission. I must have omitted this when we were looking at it the other time. So that was an omission. This is supposed to be there. I was only substituting these guys here into there. So when I substituted in and I got plus or minus 1, and maybe the speed was so high or I was too excited, I must have forgotten that. But we are saying that A dot B should not be equal to plus or minus magnitude of A, and then times magnitude of what? Of B. Or you could even just say the magnitude of A dot B should not be equal to magnitude of A times magnitude of B. The magnitude. Of course, this is just a number, but this now means its absolute value. That's what it means. But if you can remember that, it is okay. So here, if the dot product is not equal to that, then we are claiming that the angle between these two guys is neither 0, is neither 180. And so they are not on the same straight line. That was the first case. Then using now the cross product. So here, you've just proved that AB and BC are not parallel. So the moment they are not parallel, it means that these points are not collinear. This is AB cross BC. Sorry. This is AB, and then this is BC. Yeah. So you prove that AB and BC are not parallel. Then we've also looked at the cross product. How do we use it to prove that A, B, and C are not collinear? Now here we will use the aspect of area. You see, if the points are on the same straight line, A, B, and C, then the area enclosed by ABCA is 0. You're not enclosing anything. But the moment you offset that point off the line, however slight the perturbation is, we shall have a triangle. In other words, there will be some area enclosed. So the moment you can prove that the area of A enclosed in ABCA is not 0, then the points A, B, and C are forming vertices of a triangle. And how could we do that? Of course, we saw that the area, for example, if this is the triangle, this is A, B, and then C. So you could only show, you would show, because the area of the triangle defined now by the two vectors AB and AC is a half magnitude of AB and then cross BC. Even that is okay. AB cross BC, that would be now the area determined by those two vectors. It is also okay, AB cross BC. Now this should not be 0. However, since this can never be 0, so it is just even enough to show that that shouldn't be 0. The magnitude of the cross product, magnitude of that vector there. So once you can prove that this is not 0, then you can conclude that the points A, B, and C are not collinear. So here you've just proved, you're trying to use the argument that the enclosed area ABCA is not what? Is not 0, using the cross product. Remember, the area is a half times that, but you can divide both sides by a half. A half does not really affect when we have zeros there. So if this is not 0, then this only means that this guy should not be 0. That's what it means. Then the other thing we could use is the renowned triangle inequality. The renowned triangle inequality. If we have a triangle ABC, every triangle must satisfy this, that that when you add this length, when you get one length and you add to the other length, it should always be bigger than the other length. In other words, one length is always smaller than the sum of the other two lengths, which we could just write and say that AB, the length of AB, for example, should be strictly less, because if we have an equality, then there is a possibility of having collinear points. So it should be strict. That should be less than magnitude of SC. We call this the triangle inequality, and then plus magnitude of BC. So we could call this the triangle inequality. At higher levels of mathematics, there are other ways of proving this thing, but I wanted to use concepts that we are familiar with at this level, because at higher levels you may be required to prove that maybe the vectors OA, OB, and OC are linearly independent and all that kind of thing. I want to use concepts which we have at this level. So I need to emphasize something, because I have seen this in almost around three textbooks. In fact, one was published, it was published last year. AB plus, is it BC plus CA equals to 0 does not prove that A, B, and C are, I would just write affine independent, or are vertices of a triangle. It doesn't. I've seen that in around now 3 books. One was published last year, and these are very popular books with high readership. It doesn't, because here you're just proving that it's a 0 vector. This is satisfied by very, very many. It doesn't prove that the points are affine independent. It doesn't. It is even satisfied by collinear points and all that kind of. This is just the 0 vector. So that does not prove anything. So when you read, you reach that place and you're reading, just know there is a problem. When you're reading a textbook, always arm yourself with the question, where does this come from? In fact, the way I was able to identify that I had omitted this from the last discussion was someone who sent me a mail and was asking, how does it come about? Can you please explain more about that? And that's when I realized, oh, I had omitted something. So and that was very good. I like people who always follow and they arm themselves with that question, where does this come from? That's very, very healthy. Everything we do here, there is a logic behind it, and things are provable. They are not just throwing at you alien things. So I'm always arm yourself with that question, where does this come about? Where does this come from? It's very, very, very important. There are those who don't even know how to read mathematics textbooks. Someone was saying, can you give me tips on how to read mathematics? Head there, maybe I'll organize such a discussion just to talk about math, how to read mathematics, because I realize so many students don't know how to read mathematics textbooks. But one of the ingredients you must have is to arm yourself with the question, where is this coming from? The moment you can answer that question, then you're sure that you have understood what you are doing, what you are reading. Anyways, let me give you another question which you can try in a time when you're a bit happy. Prove that the points A, that is 2, 3, -1, then B, -3, 4, 6, and C, that is 4, 3, 5, are vertices of a triangle. So all you need to do is appeal to any of those results which are within the things that we know, and then you can attempt that. Okay, so we now know a lot about the dot product. We are done with the basics. Now we need to learn some very important concepts. I think we shall begin with the concept of the straight line, the lines. And we shall look at a number of concepts with these. We shall begin with what we call the vector equation of a line. Remember, now we are in 3D, in 3 dimensions. Vector equation of a line. When you looked at the straight line, perhaps in coordinate geometry, and you looked at the 2-dimensional concepts, here we are basically looking at 3-dimensional concepts, the equation of a straight line. The first one we shall look at is what we call the vector equation. So we let A, which is the point A1, A2, and then A3, be a point on the line L, R, X, Y, Z. This is like the point whose locus we are going to be looking for. X, Y, Z, be a general point. Be a general point on L. General point on L. And then also we need a vector b1 I plus b2 j plus b3 k, be a vector parallel to L. Be a vector parallel to L. So with these things, we can find a vector equation of a line. Let us assume this is our line. That's the line L. And on that line we have the point A, somewhere around there. And then of course our variable point, the point moving, that's the point R. Assuming our origin is somewhere around here, the origin, the zero vector, the 0 point. So we have the vector OA and we have the vector OR. Let us use A to denote that vector, and let us use this to denote that vector. Then of course we also have our vector B, the vector parallel to the line. That is the vector B, something parallel to line. So we notice that the vector OR, to move from O to R, that is the vector OR, this is just equal to move from O to R is the same as moving from O to A, that is OA, and then plus A to R, plus AR. But we know that OR is that vector there, and this should be equal to OA is that plus. Now AR is a vector parallel to this. And so we said, in other words, AR is a scalar multiple of that. That is, AR is equal to lambda B. So we could write this as, this is X, Y, Z is equal to A1, A2, A3, and then plus lambda, and then that means B1, B2, then B3. So that is what we call the vector equation of the line. So for each point on the line, there is a specific value of lambda which gives you that point, because remember, R is a variable point. It is describing that locus. So in other words, lambda changes for each value of R. And we could look at this as our origin, because when now you set lambda to be 0, you have the point A. You have the point A on the line. So to generate all the other points, you just vary the value of lambda like that. So we call that the vector equation of the line. So what do you need to find the vector equation of the line? We've already seen what you need. What is the most important thing you need? First of all, you need a point on the line, a given point on the line, a point on the line, and then you also need the direction of the line, the direction of the line, or the direction vector. This is what we are calling the direction vector of the line. So if you have that, then you can find the vector equation of the line. Let us pick an example. This shouldn't be a very complicated concept. Example. Find the vector equation. Find the equation of the line. Through the point. A, which is 2, 3, -2, and is parallel to the vector, and is parallel to the vector B equals to 3i plus 4j, and then plus k. So in our solution, this should be a bit obvious. We know that from r is equal to a plus lambda b. And so this means that r is going to be, a is the position vector of the known point, which is that. So we have 2, 3, -2, and then plus lambda. B is the direction of the line, which is that 3, 4, 1. And so you have the vector equation of the line, the vector equation of the line. Now sometimes the question may not be very direct like that. You may be amazed and you're like, oh, this is awfully simple. Yeah, sometimes they can choose to hide the direction of the line, they can choose to hide the starting point, but they give you enough information. But let's look at another simple example anyway. Find the vector equation. The vector equation of the line through the points. The line through the points. You have the point A, which is 1, 2, 3, and B, which is the point 4, 4, 4. Now here you realize that we don't have a direction vector. It is not directly given. So we need it. We shall look for that. So we have A and we have B. So you notice that the vector parallel to the line should be the vector AB. So we shall have the vector B as AB, which AB is going to be, of course, OB minus OA. OB minus OA. So we have 4 minus 1, which is 3, and 4 minus 2, which is 2, and then 4 minus 3, which is 1. So we have a vector parallel to our line, and therefore from R now equals to A plus lambda B, the equation of the line would then be BR equals to, we could pick any of these, either A or B, whichever, as the point on the line, 1, 2, 3, and then plus lambda times the direction vector, which is 3, 2, 1. And that would be the vector equation of your line. It should be the vector equation of your line. Time is chasing us. I guess I should use these remaining few minutes to leave you with a question, which you will try. Find the equation. A line passes through -102 and is parallel to 1 plus 3 mu I. It is parallel to the line. Line 1 plus 3 mu I, and then plus -1 plus 2 mu j, and then plus 2 plus mu k. Determine, find its equation. So you'll try out that. We can end here today in the interest of time. Thank you for staying with us. Have a nice weekend.
Somera mu ddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi tusomesa arts ne sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory ssaako ne computer lab wamu ne.
She gives you her number, but your pen didn't work and the bus is gone. Get a pen you can rely on. Big Crystal, the long-lasting pen with perfect ink flow.
Wamune.
Green Hill Academy has high standards of learning and the teachers are very good. They give you a sense of belonging.
Green Hill has helped me to discover my talent.
The environment is good.
Encouraged us children to be excellent.
Wamune.
Combo University, a private chartered university that offers world-class education at all levels, including certificates, diplomas, bachelor's and master's degrees. Our courses include computing and IT, law, journalism, nursing, business administration, education, fashion and design, and many more. Admissions for the August 2020 intake are still open. Will you join us?
Wamune.
Kids Kingdom Kindergarten and Daycare. Somero ly'abaana bato. Omuzadde leeta omwana ogenda okola ebibyo. Ebyokuzanyisa by'abaana byonna mu nsi tubirina. Ate nga abaana we bazannyira wagazi nnyo. Jjukira security enka. Amasomero gonna gali mu kikomera. Abasomesa be tulina bakugu mu baana. Abaana tubaliisa bulungi nnyo munnange. Tulina main campus e Buddo Naggalabi nga bwakayisa Buddo Junior.
Looking for a university to join? Introducing Combo University, a private chartered university that offers world-class education at all levels, including certificates, diplomas, bachelor's and master's degrees. Our courses include computing and IT, law, journalism, nursing, business administration, education, fashion and design, and many more. We also offer co-curricular activities such as sports, music, dance, and drama, and our students are among the very best athletes in the country. Admissions for the August 2020 intake are still open. Will you join us?
Tujjukira ebiseera byewagendanga mu salooni ew'omuyooyoosi wo n'akuyooyoota n'ovaawo ng'omatidde ng'olabika bulungi ng'era oli